This video will explain how to prove Einstein's theory of special relativity wrong. So why should you worry about Einstein's special relativity at all? Because it causes problems for us in terms of advancing our electrical science. If we keep teaching that light and electromagnetism are based on projectile particles, then we will continue to be stalled in advancing electrical science. This is Einstein's paper on special relativity, but realize that it's really an electrical paper. Electrodynamics meaning the movement of electricity, or today we usually use the term electromagnetics. You can see here that Einstein's special relativity is what removes the medium for electromagnetism. Now, to give an analogy for what this means, it's like looking out over a lake and seeing the waves, but then removing the medium of water. Now, when we use the word waves, it makes no sense. His theory takes away the logic for the idea of light waves or electromagnetic waves. This theory also creates weird time and space illogical behavior, or paradoxes. The popular one for time would be the twin paradox, and one for space would be the train in the tunnel. So in today's modern science, how much illogic are we willing to accept? So how is special relativity wrong? I am going to focus on two major problems with this theory. The clock paradox is a famous problem, and I learned it by reading this book. It also describes the story of all the academic dogma that surrounds Einstein's theory. But to this day, the issue of the clock paradox still remains. I think the failure of the spherical wave proof is a lesser-known problem with relativity. This is a major issue for the theory of relativity because it is actually what disproves it. In the spherical wave proof, Einstein shows that the principle of relativity is compatible with the speed of the photon. And he assumed his math was right. But when you actually check it, it is wrong. And that takes the entire theory down with it. I'll show you what I'm talking about here. So in the first part of Einstein's paper, he has to describe what he means by the principle of relativity. And then he has to connect that principle to the constant velocity of photons in empty space. He mentions here that they are seemingly incompatible, and the spherical wave proof is where he tries to make them compatible. I learned about the spherical wave proof from Stephen B. Bryant's book, and I'll show you a program that I wrote that calculates the math for the spherical wave proof. So here's a warning. Einstein's relativity can get complex and confusing in a hurry. And realize that if you are debating someone who is a relativist, they will drag you down into the weeds and create complexity in order to defend this theory. And by using complexity, they will usually say that you don't understand relativity and basically walk away from the conversation. This is why I've chosen to focus on these two major problems, and I want to stick to Einstein's own words in his own paper. The more you understand about the Doppler effect, the more you will understand how light works in its wave medium. And you'll understand the challenge that Einstein is up against when he removes this medium for light. In the medium of air, we are all familiar with these sound waves. The actual pitch of the sound of the car horn changed because it was moving relative to you. If a visible light source is moving relative to you, then you get a change in color. These changes in the pitch of sound and the color of light are described by the Doppler effect. And in this formula, the letter C stands for the propagation speed of waves in the medium. Einstein removes the medium, and now he has to get real creative in order to explain how light is going to work without a medium. In his photoelectric effect paper that was published a few months earlier, he says that the wave theory of light, which has a medium called the ether, will probably never be replaced by another theory. And then in his special relativity paper, he removes the medium for light waves and replaces it with empty space and light particles. Going back to the Doppler effect, the speed of waves in the medium is replaced with the speed of the photon particle in empty space. So now we move on to reference frames, or frames of reference. You can just think of these as types of motion. And there are just two types of motion. You're either accelerating or you're not. The reference frames that apply to special relativity are sometimes called Galilean reference frames. These reference frames deal with constant motion. Reference frames that are changing their motion, in other words, accelerating or decelerating, are known as non-Galilean reference frames. Again, the changing motion reference frames do not apply to special relativity. So remember the car horn sound example. Your reference frame would be standing still next to the road, and the car's reference frame would be moving at a constant speed right past you. These are both examples of Galilean reference frames which apply to special relativity. Even though you were standing still, that frame applies and is generally called at rest. Now, these reference frames existed before Einstein. What Einstein changed was the fact that all of these Galilean reference frames are now peer-to-peer and not in a hierarchy. Now, what the heck does that mean? I don't want to bore you with talk about reference frames, but you've got to realize that this idea is what brings a lot of illogic to this theory. It tells us that the person in the moving car can claim that they are at rest and the person on the side of the street is moving. That might sound weird, but the real problem is that there are two different answers to every problem in special relativity, and one of them is always wrong. Don't worry if you don't fully grasp the reference frames idea yet. It's pretty easy, but it's not the way we usually think of things. So we'll first look at the clock paradox, and hopefully this will start to make better sense to you. Let's dive right into the middle of relativity and talk about how time slows down, or the clock paradox. So the idea here is that you have a stationary clock and then you have a moving clock. And the moving clock will slow down compared to the clock that is at rest. Let's look at that idea in Einstein's paper. It says the clock that has been transported from point A to point B will lag behind the clock that has been at point B from the outset. And that lag time can be calculated by this formula. So he's saying that the moving clock slows down relative to the clock at rest. But in Einstein relativity, either reference frame can claim that they are at rest. So with the peer-to-peer reference frames, which clock do you apply the formula to? Which clock is actually slowing down? It makes no sense that they are both slowing down. You get two different answers here. Each clock has an answer that the other one is slowing down, but only one of those answers can be right. And that is the clock paradox, which still has not been properly answered to this day. So in the next paragraph, Einstein makes this clock paradox mistake himself. He uses an example of an at-rest clock at the equator and another at-rest clock at the South Pole. Since both clocks are at rest and neither one is moving, they should stay synchronized. So he gives another example here. If there are two synchronized clocks at point A, and you just take one of those clocks, move it around at a constant velocity, and then return it to point A, then that moved clock will lag behind the other clock that was at rest by this calculation. From this, we conclude that a balance wheel clock that is located at the Earth's equator must be very slightly slower than an absolutely identical clock that is located at one of the Earth's poles. Let's illustrate this. Two people are at rest with their synchronized clocks at a table on the equator. Now we can stretch that table all the way down to the South Pole. They're still sitting at the same table. They're both at rest. Therefore, neither clock is slowing down. Now, why did Einstein say that the clock at the Earth's equator must be running slightly slower? So according to National Geographic, the equator moves at 1,000 miles per hour, where the poles hardly move at all. Now we know that when you are sitting at a table with someone else, neither person is moving. But let's go ahead and throw that idea out and follow along with what Einstein says. When Einstein chose the clock at the equator as the moving clock, or the one that slows, at this point he is being an authority on which reference frame is moving. But Einstein relativity tells us that there is no authoritative frame. They're peer-to-peer. Either person can claim that they are at rest, and the other person is moving. So if Einstein claims that one of these clocks is moving, and that a moving clock slows down, why did he pick the clock at the equator as being the one that slows down? The clock at the equator can claim it is at rest, and the clock at the South Pole is the one that's moving, and therefore should be the one that is slowing. So now you can see that the idea of peer-to-peer reference frames creates two different answers every time. And one of those answers is obviously wrong. So Einstein threw away one of the two answers. He was the authority that chose the equator clock as moving. And he fell into his own clock paradox trap in his own paper. So then, what did Einstein himself have to say about this clock paradox? So my personal opinion, and from a scientific viewpoint, this paper is where I lost a lot of respect for Einstein. I believe he is trying to just defend his theory instead of trying to figure out what's really going on in nature. This paper was written 13 years later, and he is writing a simulated dialogue between a critic of the theory of relativity and someone who believes in the theory of relativity. So we have clock 2 moving at a constant velocity towards point B and then back to point A. Upon arrival to point A, that clock is braked. Now look what he's doing here. In his thought experiment, he is now adding in deceleration. Now he's going to talk about the clock paradox of which clock is really slowing down. So according to Einstein's relativity, the process has to occur in exactly the same way when you switch reference frames. So that means we will get a second answer when clock 1 is moving and clock 2 is at rest. So now clock 1 says it is slower than clock 2. Even the devoutest adherents of the theory cannot claim that of two clocks resting side by side, each one is slow relative to the other. So after 13 years, Einstein tries to explain this away and says the entire line of reasoning is not legitimate because one of the frames of reference in this thought experiment was accelerated. Okay, let's go with that, but it still leaves the question, how do you know which frame of reference the clock is moving slower? How do you determine which answer to throw out? Each reference frame can still claim it is at rest and sees the other person as moving and accelerating and decelerating. So does nature somehow figure out which frame of reference is accelerating? I don't know. In my opinion, it was a terrible answer. And I don't think a lot of relativists even use his answer to try to explain the paradox. Now, this clock paradox does not prove that this theory is incorrect. It just proves that there is something wrong. The failure of the spherical wave proof is what invalidates this entire theory. This proof is in section 3 of the relativity paper. From the rest system, it takes x, y, z, and time coordinates, then calculates some math, and that tells you about the reference frame that is in motion. So here are the equations that show you how to slow time and shrink space. This is the most important paragraph in this paper. It says, "For we have not yet provided the proof that the principle of the constant speed of light is compatible with the Einstein relativity principle." And that's the whole point of this paper. Remember on the first page where he says that they are seemingly incompatible. His principle of relativity and the constant speed of light. So how do we prove this? It's all right here. So when the moving system and the system at rest are at the same point in time, you send out a sphere of photons. So the rest system equation is this. Then you use the transform equations that tells you about the moving system. And the answer to this moving system equation should be a sphere when observed in the moving system. This proves that our two fundamental principles are compatible. All right, let's give it a try. So this is a simple program that I wrote in Python, and it will plot the stationary observer's view of the light sphere after 1 second of time. And let's run it. And here's the graph. So for the stationary observer, we have this sphere after 1 second of time, or 1 light second. The idea here is that the moving frame will match up perfectly with the stationary observer at 0, 0 in this coordinate system. At that point, at time 0, a light pulse goes off. And I am using the idea of light seconds, where in 1 second, it will travel the distance of 1 unit. In 2 seconds, it will travel the distance of 2 units on the graph. This is the program for the moving reference frame. Here I have it programmed to go 3/4 the speed of light, and then we'll plot the graph and see what it looks like. You can see here that the moving observer does not see a sphere. This is what disproves Einstein's special theory of relativity. You can see that the stationary observer sees the light pulse as a sphere after 1 second, but the moving observer sees an ellipse. And Einstein says right here that the moving observer should see a sphere. When you get closer to the speed of light, for instance, 98% of the speed of light, and you run the program, you can see that the ellipse becomes even more pronounced. One thing I did to try to check my work was I had my program spit out a bunch of coordinates that I could just stuff into this graphing calculator that is online. So this is the stationary observer after 1 second. So if you haven't already noticed, I've dropped the z coordinate so I don't have to work in 3 dimensions. The moving frame will be at 75% of the speed of light, and I'll run this, and all this does is spit out a bunch of coordinates that I'll just copy and paste over into the Desmos graphing calculator. And now I'll paste them in here. And all this is doing is giving me an idea that my Python graph is not doing anything weird. In other words, I'm just checking it with a different source. And as you can see here, the stationary light sphere and the moving coordinate system don't match. This is obviously an ellipse. Let's try it again at 98% the speed of light. Run the program, dump the coordinates, and copy them. Now I'll paste these into Desmos, square up the graph, zoom in, and it's pretty clear that these don't match up, and the spherical wave proof fails in Einstein's special theory of relativity. I'll put the source code in the description of the video in case you want to use it to write your own program, or just check to make sure I didn't do anything too stupid. But I have one more thing to show you before I wrap up this video. I would like to demonstrate a couple of these animations to help tie everything together. So we have 2 different frames of reference that are showing the same event. When this train car goes by this post, it sends out a light pulse. Since this is Einstein relativity, you have 2 answers, one with the boxcar moving and one with the pole moving. With the boxcar at rest, you're going to get this answer. With the pole at rest, you're going to get a different answer. And you know from what I just showed you in this video that one of these answers is wrong. Now this animation simulates if there was an ether medium at rest. This is a simulation of frames of reference prior to Einstein relativity. In the top frame, imagine that you're standing at the end of a dock and you drop a brick in the water. In the bottom frame, you are in the boat and you're looking at the dock and see the brick being dropped into the water. So on the top frame, you can watch the boat go by, and on the bottom frame, when you're in the boat, you watch the dock go by. So with the wave medium as the authoritative frame of reference, all of these events just line up naturally. So I'll leave you with that idea to think about. And at this point, the video is over. So thanks for listening.